If I draw a magnet here, a bar magnet with a bunch of domains pointing in this direction, what do we know about the polarity of this bar magnet? Which end is north, which end is south? Of course, we have to have a north end and a south end, right? We can't have two norths or two souths. Which end is north, which end is south? Left side is north? No, left side is south. The domains point from the south end to the north end. The magnetic field outside points from the north end to the south end. The magnetic fields are essentially just a continuation of the domains. So it's going to look like this. Now, you could say inside the magnetic field would be from south to north. We define the direction as being the direction that a compass points and from the north toward the south, but that's all outside of the magnet. If you're talking about inside the magnet, of course, because they just continue along in a complete circle there, the magnetic field or the domains are going to have to point from south to north. All right, so a bar magnetic field looks something like this. What if I had a charge, an electron that was just sitting there? What does the magnetic field look like surrounding that charge that's just sitting there? Not moving towards us or away from us, not moving to the right or to the left or up or down, but it's just suspended in space for whatever reason. Anyone want to answer that one? What's a trick question? It's a trick question. No. There is no magnetic field. Charges don't generate magnetic fields. Charges generate electric fields. Charges, because they're going to have mass, are also going to generate gravitational fields, albeit a smaller gravitational field than electric field. But they're not going to generate a magnetic field. What's the condition that we have to have in order for the charge to generate a magnetic field? Hans Christian Ørsted in 1819 discovered that moving charges generate magnetic fields. Stationary charges generate electric and gravitational fields because they have charge and mass. Moving charges will still generate electric fields, and they'll still generate gravitational fields, of course, because they still have charge and mass. But moving charges will also generate magnetic fields. Now, what does the magnetic field look like surrounding this negatively charged particle if it's moving in the direction indicated by that X? What does that X mean, by the way? Towards us or away from us? Austin? Yeah, it's away from us. It's into the board, or if you have it drawn on your page, it would be into your page. So this electron or negatively charged particle is going away from us into the page. The shape of the magnetic field is going to be circular, but what's the direction of the magnetic field? Clockwise or counterclockwise? What's the rule that we use to figure it out? The right foot rule? Or is it the left hand rule? Let's use a left hand rule. There's three left hand rules actually. You're going to learn a second one later today. The left hand rule that we use to determine the direction of the magnetic field produced by a moving charge is going to be called the Wiregrass Rule. In the end, the name of it is really not important. Okay, in the end, what's important is how we actually use it. Some people call it something different than the Wiregrass Rule. The book calls it Wiregrass Rule. I call it Wiregrass Rule. But in the end, as long as you can do it, it doesn't really matter what you call it. How does the Wiregrass Rule work? Well, you're going to stick your thumb. Make sure your thumb and fingers, by the way, are like spread apart. Like you don't want to put your thumb up like this, kind of parallel to your fingers. Make it as close to perpendicular as you can. Okay? And then stick your thumb in the direction of the moving charge, which is going to be into the page. Now for us, for me, that's toward the front of the room because my page is vertical. For you, that would be, if you have it drawn on your page, it would be downward toward the floor because your page is horizontal, right? So I'm going to stick my thumb into the plane of the page here, and then I'm going to bend my fingers. I can bend them as much or as little as I want. I'm probably not going to squeeze them too tight because it's a little bit hard to determine the direction of the magnetic field when you do that. Let's just bend them a little bit here, somewhere like this. Okay, when I do that, I see that, look, my fingers end up going counterclockwise around there. So the magnetic field surrounding the bar magnet is exactly what we would have saw a couple of days ago. The magnetic field surrounding this moving charge is circular, and it's going to be counterclockwise. What if we had a positive particle, an alpha particle, proton moving through the air, maybe is indicated by the dot, which means, of course, towards us. The magnetic field is still going to be circular. Still going to be circular, but what direction is it going to be in? Well, this time you're going to use your right-hand rule. Okay, that's something you probably should see a question that says an alpha particle. Circle it in red to remind you that it's a positive particle and to remind you that you're going to use your right hand to determine the direction of the field. Thumb in the direction of the particle, which is, in this case, out of the plane of the page. For me, it's toward the back of the room because my page is vertical. For you, it's toward the ceiling because your page is horizontal. Thumb, fingers, you're going to go counterclockwise again. In both cases, counterclockwise. Here's one for you. What if those two particles are actually interacting with each other? So they're close enough together. They're not independent events like I have them drawn here. They're a little bit closer together, like this, and they affect each other. When I have two magnetic fields, there will be a force that acts between them. It's like when I put another magnet nearby this thing, there's going to be a force between that magnet and the other magnet. It's going to be attraction if it's opposite poles. It's going to be repulsion if it's like poles. Field lines join up. It's going to be attraction. If the field lines don't join up, it's going to be repulsion. What about these two moving charges? They both produce magnetic fields. There should be, because there's two magnetic fields in interaction, or a force between the two. What kind of force is it going to be? Attractive force or repulsive force? That's a tough question. That's a tough question. Let me give you a second to think about that, okay, at your desks. Give it some thought. Try to come up with a reason as to whether it's attractive force between these two particles or repulsive force. Now, keep in mind, we're not talking about the electric force, right? One's a positive particle, one's a negative particle. The electric force will be attractive for sure. But what about the magnetic force? Is it going to be attractive or repulsive? All right, let's go through the reasoning that we use to determine, or the reasoning that I use at least, to determine whether this is attractive or repulsive. Allie said at the back of the room, she said, these field lines kind of go in the same direction, so they kind of join up. She's kind of saying like, look, here's a field line, here's a field line, kind of goes like this, kind of goes like this. Okay, seems to work, right? Field lines join up, it's an attractive force. But then right here, it seems like almost like, wait a sec, they're kind of going against each other. So what does it end up being? Well, Allie's actually right. Okay, here's the deal. The field lines, if you were to draw these field lines interacting, they would actually end up looking like this, where they join up like this and end up making an attractive force because they join up. But that's a little bit hard sometimes for us to kind of see, you know, what's going to happen to the field lines in between. I'm not sure that if I was in grade 12, I would have actually caught that. So let me give you another way of determining whether this is an attractive or repulsive force. Let's pretend for a second these field lines are not the result of moving electrons or moving alpha particles. Let's pretend the result of bar magnets. Let's draw a little bar magnet right here, a pretend bar magnet right there, that generates a magnetic field that goes from the north around to the south, and then inside, of course, from the south to the north. Let's pretend this is a little bar magnet. They're not bar magnets, but we can pretend they are for a second. Okay, the magnetic field goes from the north around to the south right here. We got a south pole against the north pole, they're going to attract, right? What if you drew your little pretend magnet somewhere else? What if you drew them down here? Well, the magnetic field goes this way. Here's south, here's north. Here's south, here's north. Well, we got north against south. It's still going to attract. Well, what if we drew our little bar magnets right here? Okay, magnetic field goes this way. This is south, this is north. Okay, magnetic field goes this way. This is south, this is north. They're still going to attract, right? North against south, south against north. So any way you look at it, if you have two charges that are opposite and they're moving in opposite directions, there's going to be an attractive magnetic force. But I'm telling you guys, don't memorize that. Don't memorize that opposite charges moving in opposite directions produce an attractive magnetic force, because you got opposite charges moving in opposite directions, opposite charges moving in the same direction, like charges moving in the same. It just gets way too confusing to memorize that. Just be able to go through the logic that either Ali went through or I went through here to determine that that's an attractive force, or that a slightly different scenario might be a repulsive force. Does that make sense to everybody though? All right, remember, always going to be an attractive electric force, always going to be an attractive gravitational force, although an incredibly small gravitational force because the masses are so small. May be attractive, maybe a repulsive magnetic force. All right, let's do one more quick one here. The one that everybody seems to have some trouble with. Let's say we've got an electron or electrons moving through a wire to the left side of the page. We want to know the direction of the magnetic field above the wire, below the wire, in front of the wire, and behind the wire. Same hand rule, right? Wiregrass rule. Thumb in the direction of the particle, like this, towards the left side of the room. Okay, wrap our fingers around here. This is the wire. Right now my fingers are in front of the wire and they're pointing toward the bottom of the page. Right now they're below the wire, they're pointing into the page. Right now they're behind the wire and they're pointing toward the top of the page. And right now they're above the wire and they're pointing, if this is the plane of my page, out of the page. Right? As I was walking around yesterday when you guys were doing this, there's lots of people like sticking their thumb in crazy directions. Like, guys, like if you have an arrow saying the particle is moving this way, stick your thumb that way. Okay, if the particle is moving to the left side of the page, then literally put your hand on the page and stick your thumb to the left. Okay, don't try saying, oh, that looks like it's kind of up. No, it's to the left of the page. Okay, make it to the left. Put your thumb in the direction of that particle. Right? We're going to have ourselves a little quiz tomorrow on the introduction to magnetism stuff, up to and including the Oersted Wiregrass Rule. Okay, so if you're good with what we've done so far, then you should be good with tomorrow's quiz. I want to teach you a new rule today, though. We're going to call it the Coil Rule for solenoids. What the heck is a solenoid? Well, a solenoid is a coil of wire. If a wire that has an electric current going through it generates a magnetic field, then a loop of wire or a coil of wire, a solenoid, will also generate a magnetic field, because all it really is wire with an electric current going through it. But because the wire is looped around, looped around, looped around, the magnetic field actually gets magnified. Each loop of the solenoid generates a magnetic field. So if you have the loops going around in the same direction, then the magnetic field caused by one loop adds to the magnetic field caused by the next loop, adds to the magnetic field caused to the next loop, and so on and so on and so on, magnifying the effect of it. If we just have a straight wire, each part of the wire generates the same magnetic field, but they don't loop back upon themselves to magnify the effect of it. So you got a solenoid, a coil of wire, you get a magnified magnetic field, a more pronounced magnetic field. Now generally, although not always, inside a solenoid or a coil of wire, you're going to have what we call a soft iron core, okay, or a ferromagnetic material. Soft iron, by the way, doesn't mean iron that's kind of squishy, like a pillow. Soft iron means a temporary magnet. A soft magnet is a temporary magnet. A hard magnet is a permanent magnet. So generally what you have inside here is a soft magnet, something that can become magnetized. That kind of stores the magnetic effect that's caused by the moving charges in the wire. So you got all these wires, all this wire wrapped around something that's ferromagnetic, a piece of soft magnet, okay, a piece of steel, a piece of iron, whatever, that's not magnetized right now, but has the potential to become magnetized. This loop of wire generates a magnetic field and gets stored in that piece of steel. This loop of wire generates a magnetic field, gets stored in this piece of steel, and so on and so on and so on. Ultimately, it ends up turning this piece of steel into a magnet, an electromagnet. Right? That's the electromagnet that we talked about the other day that a couple of you made when you were in grade 4 or grade 5 when you did electricity in elementary school. Here's what we want to do today, though. We want to figure out what the polarity of this electromagnet is. Okay, we want to figure out which end ends up being a north and which end ends up being a south. I'm going to remind you first how the Wiregrass Rule works, because I'm going to go back to it, because this is real similar to the Wiregrass Rule, but with a fundamental difference here. The Wiregrass Rule is used to find the magnetic field caused by a moving charge in or not in a wire. You've got two variables here. You got your thumb. You're going to stick your thumb in the direction of the moving charge. And you've got your bent fingers that you're going to stick in the direction of the magnetic field. You guys remember that's the symbol for magnetic field? The magnetic field caused by the moving charge. Now, the coil rule is going to work with the same two variables, but it's going to work exactly opposite to the Wiregrass rule. Your thumb is going to point in the direction of the magnetic field caused by the solenoid, of course, which ultimately is moving charges. And your bent fingers are going to point in the direction of the moving charge. Well, in the context of a solenoid, that moving charge is going to be an electric current. So thumb, charge, fingers, magnetic field. And then the next one's going to be fingers, charge, moving charges, thumb, the direction of the magnetic field. I'm going to draw a picture of a solenoid right now, and we're going to use this rule to determine what the polarity of that solenoid is. Which end is north pole, which end is south pole. Here's my soft iron core, or my ferromagnetic material that's not magnetized right now, the thing that I want to turn into a magnet. Here's a wire wrapped around it. Now, just watch what I'm doing before you draw this, okay? You see I've got it looped around, but you see what I've got? I've got it looped around in the front right here, and then it kind of goes down to the back. And then it goes up in the front right there, and then the back, and then the front, and so on. And then it kind of loops around the back for my final loop. Does that make sense? I've got a battery attached here. The battery has a negative terminal and a positive terminal. Same rule applies to the battery as when we drew the battery for the parallel plates. Okay? Positive terminal and negative terminal. The short end is negative, the long end is positive. That battery generates an electric current, and we know which direction the electric current flows. It's going to flow clockwise here because it leaves the negative end and it goes around to the positive end. So it's going to go up in the front, and then it's going to go down in the back, and then it's going to loop back up in the front and down in the back, and then back up, and so on and so on and so on. So in all these loops, the current is going to go up in the front, down in the back. We don't need a hand rule to determine that. We know that it's going to go that way simply because of the way the battery is set up. That electric current generates a magnetic field everywhere. Everywhere that electric current is in that wire, it generates a magnetic field, which gets stored in this ferromagnetic material inside the core. You could use the Wiregrass rule to determine the polarity of this, but the coil rule is easier. So that's what we're going to use. Here's what I'd like you to do right now. Yesterday, or a couple of days ago, we did a lot of activity where we connected some dots, a little kindergarten or grade 1 activity where we connected some dots to determine what the magnetic field will look like surrounding bar magnets. Today we're going to do another little elementary school activity. I'd like you to take a piece of paper right now. If you don't have scrap paper there, just take a piece of scrap paper from here and roll it up, coil it up, like this. Now I want you on your coil to label it front. I want you to literally to take a pen and write the word front on that coil. It doesn't matter where you write it. write it somewhere so you can read the word front. Now, when I'm demonstrating this, you're going to be looking at the front of my coil. I'm actually going to be looking at the back of my coil, the back of my solenoid. Okay, the reason I want you to write the word front on is so that we're under the same frame of reference, so the same understanding as to which is the front, which is the back. Okay, you're looking at the front of my coil. You also need to be looking at the front of your coil. That's why we have it labeled front, so we know which side we're looking at. Some people, for whatever reason, whenever I've done this in the past, they're looking at their coil and they get mixed up between which is the front and which is the back. Okay, we're labeling the front and you're looking at the front of the coil. Now remember how the Wiregrass Rule works, the Coil Rule works. It says opposite to the Wiregrass Rule, thumb goes in the direction of the magnetic field, fingers go in the direction of the electric current. In front of this coil, the electric current goes up. You need to stick your fingers, the ends of your fingers right now, in front of the coil. Okay, remember, you've got it labeled front, so you know where the front is. Wherever you have the word front labeled, touch it with the tips of your fingers so that your fingers are pointing up. Make sure you're using your left hand because we're talking about electron current here, the flow of negative charges. Okay, where you see the word front, the part that you're looking at, touch it with the tips of your fingers. Then bend your hand around like this. So now my fingers are bent. They're in the front and they're pointing upwards, just like this, right? Current is going upwards, my fingers are pointing upwards. Which way is my thumb automatically pointing? If you're looking at the front, which way is my thumb automatically pointing? To the right. That means the magnetic field inside this coil is to the right. What's the polarity of this coil going to be if the magnetic field inside is to the right? This end is going to be north or south? South. And this end is going to be north. You guys remember the bar magnet? South pole, north pole. The magnetic field inside, or in other words, the domains inside are going from south to north. Outside it's north to south, but we're looking at the magnetic field inside here. So once again, you're looking at this coil, you're looking at the word front, you stick your fingertips on the word front pointing up because the current is pointing up in the front, you bend your fingers around and your thumb points to the right. The magnetic field inside is to the right, which means the left side is south and the right side is north. Does that make sense? Okay, we're going to do another one. Here's my soft iron core or my ferromagnetic material inside. Here's my wire. Here's my battery. Which end is the positive end? Which end is the negative side of the battery? This side is what? Positive or negative? Positive. This side is negative. Current's going to go which way? It's going to go this way? No. Going to leave the negative end. Going to leave the negative end and go around towards the positive end. So it's going to always leave that negative end here. So it ends up going up in behind the piece of steel and then down in the front. Up in the back, down in the front. Up in the back, down in the front. So it's kind of opposite to what it was, right? In the last one, it was going up in the front. This time it's going down in the front. Okay. If you're looking at your coil again that you just made, you're looking at the word front. Okay, you're staring at the word front. You're sticking your fingers on the word front, your fingertips, your fingernails on the word front. But they have to be pointing downwards because the current is down in the front here, right? Down in the front, literally. Bend your fingers around. Your thumb is going to point which way? Remember, you got to look at the word front, right? Yep. So don't keep turning your hand around like this. Okay, which way does your thumb point now? Thumb points to the left. So the magnetic field inside here, because my thumb is pointing to the left, is going to look like this. That means this end is south, and this end is north. Make sense? Okay, I'm going to go back to the last one we drew here. Draw another one right beside it here. Which end is positive, which end is negative? Not sure which side is positive, which side is negative. Good. The left is negative, the right side is positive. Which way is the current going to go around here? Counterclockwise like this or clockwise like this? Sorry? Clockwise. It leaves the negative end, goes around towards the positive end. Look, it's the same thing as we had right here, right? Answer should be exactly the same, right? What's different about this diagram than this diagram? Are we going to get the exact same magnetic field? Yeah, the wire starts off behind the piece of steel instead of in front of the piece of steel. So you can see that the current is still going up clockwise, but it means this time, because of the way the wire is set up, it's going up in the back, down in the front, up in the back, down in the front, up in the back, down in the front. Unlike the other one where it was going up in the front, down in the back. All right, that's okay. It's not a big deal. It just means that because there's so many different possibilities here of which way the wire is oriented, which way the current is going, means that you don't want to memorize it because you're going to end up messing up if you memorize it. It means you want to figure it out every time, like that example we did of the two wires. You want to figure it out every time. All right, so again, you're looking at your coil. You got the word front printed on the coil, and this time we want our fingertips touching the word front again, pointing down. My fingertips have to point down in the front. My thumb is automatically going to point to the left. Now, as I'm watching you guys with your little handy elementary school manipulatives here, like I see people doing this, like no, don't do that. Look at the word front. Okay, make sure you can see the word front on your coil the whole time. If you turn it and you can't see the word front, you've done it wrong. You need to see the word front, and you need to put your fingertips over top of that word front, and then not turn your coil around. Just know that your thumb, is pointing to the left, which means the magnetic field is this way. It means this end is south, this end is north. So although we get the current clockwise in both cases here, we get an electromagnet produced with opposite polarity. Question, go ahead. That's a good question. Let me come back to that in just a second, okay? Question for you before I answer that question. Provide me with two ways that I could produce a stronger electromagnet. Okay, this is going to pick up, let's say this is the electromagnet in a junkyard. You guys have all seen that on TV, right? The electromagnet picks up a car, okay, takes it over here, drops it over here, gets put in a crusher or whatever, right? Give me two ways that I could produce a stronger electromagnet than what I have right there. What's one way? Yep. More loops of wire, right? More loops of wire in the coil. So instead of having, 1, 2, 3, 4, 5, 6, 7, 8 coils or loops of wire, maybe I've got 16. That makes my electromagnet twice as strong. It's literally a 1-to-1 ratio, right? If you double the number of loops, then you double the strength of the electromagnet. Yep. Yeah, you up the current, basically, okay? You have a bigger potential difference, which causes more electrons to flow through there, a stronger electric current, which is going to produce a stronger magnetic field, and it's going to produce a stronger magnet. Okay? Jacob just asked a question a minute ago. He said, do we always use the left hand for this? For these ones, it would be 99 times out of 100 that you would use your left hand. I'm going to define a couple terms for you that you rarely have to use, but occasionally do pop up. And that's going to distinguish between the 99 times you use your left hand and the 1 time that you use your right hand. Electron current versus conventional current. Electron current is the flow of electrons. And that's the way current really flows. It's electrons that move. We know it is because, of course, we learned in our last unit, protons can't move. Protons are too tightly bound to the nucleus. Electrons can move around this circuit and with a little bit of energy supplied to them, we have an electric current. powers a light bulb, makes an electromagnet, whatever. Conventional current is the flow of positive charge. Now, we can have positive charge flowing. An alpha particle could be moving through the air. That's conventional current. A positive ion could be moving through water. That's conventional current. But protons themselves don't move. So if you're talking about a wire, you would normally be talking about electron current. Now, having said that, we didn't used to understand how electric current worked, right? In 1819, Hans Christian Ørsted discovered that electric current generates a magnetic field. But we didn't even know in 1819 what electric current was. We didn't know that it was the flow of electrons. So for a long time, it was assumed that positive charge flowed. So they used conventional current. When they analyzed anything, they did it in terms of conventional current. We assumed positive charge flowed. Now, it didn't, but the reality is it works. So here's the deal. If I say analyze this using electron current, well, we would say the negatives flow clockwise. Let's look at the first one here, okay? Again, the negatives flow clockwise, and that would mean that I would have to stick my fingers goes up in the front, right? Again, the word front, fingertips go up in the front, thumb points toward the right side, south pole and north pole. If I said analyze this using conventional current, the flow of positives, even though positives don't really flow in there, it still works. If I said analyze it using conventional current, then the conventional current, the flow of positives, if it could really do that, would go the opposite way. It would go up in the back, down in the front. We would use our right hand, because it's conventional current, right fingertips down in the front, which is my thumb point, still points to the right. That makes sense? So it's okay to use electron current, and it's okay to use conventional current. But I understand if you're using conventional current, you'll get the same answer. Just make sure you use your right hand for that. Just be consistent. Using electron current, great, left hand. Conventional current, fine. Even though it's not really the way it goes, it's fine, it still works. Just make sure you use your right hand for it. Okay, I'm going to give you one to work on yourselves here now for a moment here. Here's my my ferromagnetic material here. Here's my loops of wire wrapping around to produce a solenoid. And here's my battery. I want you to determine the polarity of this coil now. Which end is north, which end is south? Okay, let's have a look here so we can break up the fight between Nick and Alora here. All right, so which way do we have the current going here? Assuming we're talking about, Jacob, electron current, which is going from negative to positive, it's going to go this way, right? Now, if we're talking about conventional current, it would go the other way around, right? We just have to make sure we used our left hand, or sorry, our right hand. So electron current is going to go this way. It's going to go to the left and behind, then around to the right, to the left, to the right, and so on. Comes back around to the battery this way. All right? Goes clockwise. Now, that doesn't tell us anything right now about which end is north and which end is south. Okay, some of us try to remember, oh, if it's clockwise, then this end is north, this end is south. Don't do that, because depending upon how the wire is set up, okay, it could be the opposite of that. Do it every time. Figure it out every time. Let's look at your little elementary school manipulative again. You're looking at the word front on my coil. You're looking at the word front on your coil as well. My fingers need to point towards the right side, but they have to touch the word front. So my fingertips, literally put them on the word front. Loop them around here. Thumb points which way? Thumb points down. Right? So that means the magnetic field inside the coil is going to point down, which means this is going to be a south pole and this is going to be a north pole. How many people got that? What were you guys doing fighting about it then if you guys both agreed? Let's try one more here. This one's going to be a little bit different though. This time we're going to have coil of wire going around like this. We're going to have a battery set up like this. Oops, we're not going to have a battery set up like that necessarily. We're going to have the north pole of a magnet right there and the south pole right there. Now keep in mind, that's not a magnet that we put inside there. That's a magnet that was produced by an electric current. It's an electromagnet. I'm just working backwards this time. Instead of saying, here's the current, what's the polarity of the coil, I'm saying, here's the polarity, what's the direction of the current. So I want you guys to draw for me the battery down here. Does the battery go this way, or does the battery go this way? Okay, let's have a look at this one now. What do we know about this? Well, we don't know the direction of the current, but we want to find the direction of the current. What do we know about this, though, Laura? Wait. What do we know about this? Well, we know that the north pole is on the left side, the south pole is on the right side. That means the magnetic field inside is pointing which way? Outside, it points from north to south. Inside the coil, or inside a magnet, it points from south to north. So the magnetic field goes this way. Now, we take our coil that we made, our little handy-dandy, trusty elementary school manipulative here. We look at the word front again, because we're always looking at the word front. Don't know where to put our fingertips, but we do know to put our thumb towards the left side. So thumb's pointing to the left. Now, make sure now, as you put your thumb to the left and as you bend your fingers, that your fingertips are in the front. Now, which way are they pointing? Well, whichever way they have to point. If you put your thumb to the left and you bend your fingertips around, unless you can somehow bend your fingers the other way like that, they have to be pointing down in the front. Does that make sense? They have to be pointing down in the front. That means the electric current is down in the front, up in the back. Down in the front, up in the back. The electric current ends up going this way, which means my battery is going to look like this. How many people got that? Good. I'm going to finish off the day here with just a couple of applications of this whole magnetism from electricity thing. Remember we said yesterday when we introduced it, 1819, Hans Christian Ørsted makes, in my mind, one of the most important scientific and technological discoveries in the history of the world. There's got to be applications for it, right? There's more than a million applications for it. The first one is speaker. This is the speaker that you have in your car, the speaker that you have in the stereo in your house. It's the speaker that you have in your earbud, just on a much smaller scale. How does it work? Well, sound is actually compressions and rarefactions. You remember that term for Physics 20? Compressions and rarefactions for longitudinal waves. Areas of high pressure and then areas of low pressure that follow it. They kind of roughly correspond to crests and troughs in waves. That's what sound is. Well, sound is generated, or sound can be generated at least, by a piece of fabric or a piece of cardboard or a piece of felt that we call a cone. And as that piece of felt or cardboard or whatever it is vibrates back and forth, it causes compressions and rarefactions in the air. It causes high pressure areas and low pressure areas in the air. And those high pressure areas and low pressure areas get interpreted by your eardrum as sound. Well, how do we make this cone vibrate back and forth to produce these high pressure areas and low pressure areas to produce this sound? Well, it's electrical and it's magnetic. We've got a permanent magnet. We've got a permanent magnet that's yellow here that's set up attached to the cone. So this permanent magnet is attached to the cone. If you ever open up a speaker, you'll see that. It's a pretty strong permanent magnet, actually, that's attached to this cone. Now, kind of depends upon how the speaker is designed, how exactly it's set up, but it's more or less going to be set up in the way that it's set up here, where you have this coil that's wrapped around. So in other words, you have this solenoid that's got an electric current going through it. That electric current is coming from your iPhone. It's coming from your stereo. It's coming from whatever it is that's generating the sound, the radio, whatever it is. Okay? The signal, there's an electrical signal that comes from your stereo, there's an electrical signal that comes from your radio, from your iPhone, and whatever, that generates a magnetic field in this coil. It's got a polarity, a north pole and a south pole. What does that do? Well, it either attracts or repels the permanent magnet. So it either moves the permanent magnet this way, or it moves the permanent magnet this way, depending upon the direction at any one given moment of the electric current in this coil. So as we apply an electric current through this coil, an electric current that varies all the time, right? Many cycles per second. Sometimes it's going this way, sometimes it's going this way, whatever. As the electric current varies in direction and in strength, it causes the permanent magnet to go this way or this way at varying speeds. As that permanent magnet goes this way or this way, then that's going to pull with it or push with it this cone and cause these vibrations in the air, these high pressure areas and these low pressure areas in the air. How is this based on what we've learned here, this discovery by Oersted that electricity generates magnetism? Well, if you don't have a magnetism, if you don't have a polarity of this coil, of this solenoid that's generated when electricity goes through it, then it's not going to do anything to the permanent magnet. And therefore, it's not going to do anything to the cone, and you're not going to get any sound out of it. All you got coming out of your radio is electricity. And you can't interpret that as sound unless electricity generates magnetism. Listen, are you ever going to have to describe the operation of a speaker on a test? Not likely. Are you ever going to have to interpret the operation of some technological device that you've never seen before on a test? Yeah, sure. Work through it like we just did using the principles that we've learned over the last couple of days. Here's another one. What do you think this is? What is it? Yeah, it's like a bell or an alarm. It could be a fire alarm. It could be a doorbell. Most doorbells don't work like this, right? Most doorbells, you press the button, it goes ding dong, right? But I remember when I was a little kid, I had a friend that had a doorbell like this. It would be like a fire alarm almost, except it only rang as long as you held on to it, right? And so it wasn't like press it and then like a fire alarm going off in his house. You would press it and it would ring, 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 and then you let go of it and it would stop, right? It's like this, right? How does this work? Well, if you can see this clearly, we've got a switch here which turns on or off the electric current. Right now the switch is open. If the switch is open, then that means the electric current is not going to flow around the circuit. If the switch is closed, then the electric current will flow around the circuit. Let's close it. Switch is closed now. We've got a battery with a negative side and a positive side. The electric current is going to go around this way. As the electric current goes through this thing that we call a make or break contact, right now it's made, it's touching. It's going to go through this little thing that's attached to a spring here. I don't know how well you can see that from where you are. Go through here. It's going to go through here, around these coils, around these solenoids, and back around here. All right. So now, as we have an electric current going through these solenoids, it generates a magnetic field. It produces a polarity. Okay, these become electromagnets, these two solenoids. As they become electromagnets, they attract this thing right here. They attract this piece of steel right here, which pulls with it, as it's attracted to the electromagnet, this hammer. So as this red piece of steel gets attracted towards these electromagnets, the hammer hits the bell. What do you hear? Ding. That's it. That's not a very good fire alarm, not a very good doorbell, if all I hear is a ding. But what happens when this red piece of steel here gets attracted to this electromagnet and I hear the ding? The make or break contact is broken. So the current stops flowing. The switch is still closed, but the current stops flowing because it's not a complete circuit down here. When the current stops flowing, what's going to happen to all this? Magnetic field disappears. The little spring we have here pulls back this red piece of steel. The hammer gets pulled back this way. Contact is made again now. Electric current starts flowing. The cycle repeats itself. Electromagnets attract the red piece of steel. Hammer goes with it. Ding. Contact is broken. Current stops. Spring pulls the red piece of steel back. And of course, the cycle keeps repeating itself over and over and over again, probably dozens of times per second. Ding, 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 as opposed to just the one ding. Make sense? You ever going to see this one on a test? Probably not. But we got to be able to interpret novel things based on the principles that we've learned. Got a couple multiple choice questions for you, okay? And then we're going to wrap it up for the day here. Take a look, please, at question number 66. You can look at it on the board, or you can take a look in your worksheet booklet here. All right, so what do we got here? Which ones are they going to repel in? Okay, what are we looking for here? Okay, don't look at the options yet. Okay, what are we really looking for here? How are we going to tell whether things repel or attract? If we know what the poles are, easy, right? North pole, south pole, attract, north pole, repel. But we don't have the poles here. How do we know which ones are going to repel in this diagram? Yep. Good, when the field lines don't join up. So this one's out because the field lines join up there. This one looks like it repels because the field lines don't seem to join up. This one, field lines join up, going to attract. This one, the field lines don't join up, so they're going to repel. So our answer is that 2 and 4? Yeah. Options 2 and 4. Options 2 and 4D. How many people got that one? Good. Excellent. Another one. This question looks remarkably like a question that we saw on our unit test, our electricity unit test, and on our electricity unit assignment, except it was electric fields, not magnetic fields. We do the same thing though, right? Look, the electric field away from a positive charge would be this way. Well, the magnetic field from a north pole goes upwards as well. Goes to the right towards the south pole. The magnetic field ends up going somewhere in between there, about like this. So the direction of the magnetic field would look like D here. Okay, one more, and then we're done for the day. Number 69, please. By the way, if you can't make these out, these are supposed to be compasses, and the compass needles are pointing like this. It's just kind of a little bit hard to see them here. Okay, what do we do here? Well, bottom line is we got to know two things here, right? Two things. One, we have to understand that the direction of the magnetic field is the direction that a compass will point. Compasses point in the direction of the magnetic field. Okay, secondly, we have to figure out what the direction of the magnetic field is by the Wiregrass Rule. So let's stick our thumb in the direction of the electrons, which is up toward the top of the page. Fingers go around like this. Means that if this is my wire here, my fingers in front of the wire point towards the left. So my fingers here should point this way. Well, that's not which way the compass points. Okay, compass should point in the direction of my fingers, the direction of the magnetic field. So this one doesn't work. What about to the right of it? Sorry, to the left of it? Fingers are pointing into the page there. So my magnetic field should point this way. Well, they've got it shown pointing outwards, so that doesn't work. Behind the wire, my fingers point to the right. They've got it pointing out of the page. That doesn't seem to work. They must be the last one, but let's check it. Okay, to the right of the wire, my fingers are pointing out of the page. Which way is the compass pointing? Out of the page. So this is the one that shows the correct direction of the magnetic field, option 3. How many people said that one? Good. All right, here's your homework for tonight. Some check and reflect questions on page 592. I want you please to do question number 2, 5 to 8, and 10 to 16, please.